Hi Year 13, this lesson we are going to continue with our energy cycle studies, but rather than use delta HF like we did in the last lesson, we are going to use delta HC values. Now a quick refresher of the definition. The definition of the delta HC, the standard enthalpy of combustion, is the enthalpy change when 1 mole, and the 1 mole is really important, of a compound is burned completely in oxygen under standard conditions. We're going to use Hess's law again, so again a quick refresher. Hess's law states that the enthalpy change is independent of the route taken, provided the initial and final conditions are the same. Now if we consider example 1 on page 47, we are asked to work out the enthalpy of formation of methane, but we are given 3 delta HC values. Now let's just revise what these delta HC values are. So the delta HC of carbon is when we burn 1 mole of carbon, and state symbols are important, in oxygen to form 1 mole of carbon dioxide. But it's important that we burn 1 mole. We've just formed 1 mole here by chance. The second equation then is for the delta HC of hydrogen. So we are burning 1 mole of hydrogen in oxygen to form 1 mole of water. Now we've got to burn the 1 mole of hydrogen. We've got to keep it balanced, so we actually only need half a molecule of water. The last one then is the delta HC for methane. So we are going to burn 1 mole of methane in oxygen to form carbon dioxide and water. Now we've got to be very careful that we keep the 1 mole of methane, but we've also got to make sure that the equation is balanced, and water is a gas at room temperature and pressure. So I will need to balance it with a 2 here and a 2 here. Now it would be a good idea to write those equations into your notes. Now we're asked to work out the enthalpy of formation of methane. So remember, your definition for the delta HF is that it's the enthalpy change when we form 1 mole of a compound from its constituent elements in their standard states. So the equation that I have just written is for the delta HF of methane. And this is our unknown, and as before, this should be the top line in our cycle. So this is what we want to find. Now last lesson, we were given delta HF values. We listed elements at the bottom of the cycle and our arrows pointed up. This time we're given delta HC values, so we are going to burn each of these elements or compounds to form their combustion product. So I'm going to burn carbon as per the blue equation to form carbon dioxide. I'm going to burn hydrogen as per the green equation to form water. Then I'm going to burn methane as per the red equation to form carbon dioxide and water. I'm just going to be careful because I would actually form 2 moles of water. Now this blue equation represents the delta HC for carbon. The green equation represents the delta HC for hydrogen, but be careful, it's 2 times this delta HC because there are 2 molecules of hydrogen. The red arrow represents the delta HC for methane. Now here is the indirect route, or the direct route, apologies. Here is the indirect route. Now Hess's law states that the enthalpy change will be the same regardless of the route that we take. So we're going to take the indirect route. So the delta HF that we're trying to find for methane will be equal to, now it's very important that we follow the yellow arrow and we see whether it's going in the same direction as the other arrows. So up until here, it's going in the same direction as the blue and the green arrow. So the delta HF will be equal to the delta HC for carbon plus 2 times the delta HC for hydrogen. But be careful, when we get to here, we are going against the direction of the red arrow. So therefore, it will be minus the delta HC for methane. Now, if we pop the values in that we're given, minus 394 plus 2 times minus 286 minus negative 890. And when we go ahead and solve that, minus 394 minus 57. 2 minuses make a plus, so plus 890. Our final answer then, when we solve it, comes out at minus 76 kilojoules per mole. Now folks, if we keep working and we consider example 2 on page 48. Now again, if you look at the information that we're given, we are given values for delta HC. Okay, we've got the delta HC of carbon, the delta HC of hydrogen, and the delta HC of this ethanol. We are asked to calculate the enthalpy of formation of ethanol. So this is what goes on our top line, an equation to show this delta HF. And being very careful that we balance it to always keep 1 mole of the ethanol. Now we're going to burn carbon, 2 atoms of carbon to form carbon dioxide. Then we're burning 3 molecules of hydrogen to form our water. We're also then burning our ethanol, that's a type of mistake, to form this carbon dioxide and water also. Now when we solve it then, here is our direct route and here is our indirect route. So the delta HF of ethanol will be equal to 2 times our delta HC of carbon. We're going with the arrow again, so plus 3 times the delta HF of hydrogen, minus then, because we're going against the last arrow, the delta HC of ethanol. Then when we go and we pop in our numbers and we solve, we see that the answer comes out at minus 273. So it's important always to remember that if we're given delta HC values, our arrows point down to form these combustion products. We have a shortcut. We do need to be able to draw the cycles, but the shortcut is useful in that it can be used as a bit of a check at the end. Now there's a bit of a typo in your note, so just correct it with me now. If we're using the shortcut, the delta H of the reaction, when we're using delta HC values, will always be the sum of the delta HC of the reactants minus the sum of the delta HC of the products. And if you were to use that shortcut for example 2, you'll find that it comes out with exactly the same answer, and perhaps it is a useful check. Now the downside with the shortcut is that when we were using delta HF values, it's the sum of the delta HF of the products take away the sum of the delta HF of the reactants. So you've got to be careful that you get it the right way round if you're using the shortcut. But as I say, the cycles are the best way because it's better for A2. Now before we leave it, let's just look at number 1 on page 49. Now again, we are given these delta HC values. And it's important that we remember that we're using delta HC. We're using what the question gives us. We're expecting our arrows to point down. We're told to find the delta HF of butane. So let's write the equation for the delta HF of this butane. So it's formed from carbon and hydrogen. It's an alkene and it's C4H10. We'll pop in our state symbols. We need to form 1 mole of it, but we've got to make sure that it's balanced. Now this is what we want to find, and this is a delta HF value. I'm going to burn carbon first of all to form carbon dioxide. I'm going to burn hydrogen then. There are 5 of them, so we will form 5 waters. And there were 4 carbon, so we'll form 4 carbon dioxide. Then we'll burn this butane to form carbon dioxide and water. Now, the red arrow is the delta HC for carbon, but there are 4 of them, so it's 4 times minus 394. The blue arrow is the delta HC for hydrogen, but there are 5 of them, so it's 5 times minus 286. The black arrow is the delta HC for butane, so it is minus 2877. Now when I go to solve, there is the direct route, there's the indirect route, the delta HF that I want to solve then will be equal to, we're going with the direction of the red arrow, so 4 times minus 394. We're going with the direction of the blue arrow, so 5 times minus 286. We're going against the direction of the black arrow, so minus negative 2877. Then when I solve, minus 1576 minus 1430, 2 minuses make a positive, so plus 2877. The answer comes out at minus 129 kilojoules per mole.